Okay, dear students, I am Dr. Srinivasan from Freshman Engineering Chemistry Department, Institute of Aeronautical Engineering. So we have seen in the last video electrochemical corrosion mechanism, chemical corrosion mechanism. Before that, we have seen the introduction to corrosion, what is corrosion, why it occurs in the metal, etc. So in today's video session, we will see corrosion and its different types of corrosion and factors affecting the corrosion and cathodic protection. Okay. So corrosion types, we have seen already two different types, and inside the electrochemical corrosion, there are further types of corrosion, two different types. So types here means types of corrosion, electrochemical corrosion, because electrochemical corrosion is the maximum cause with which corrosion is formed in nature. Okay. And factors affecting the corrosion. So some factors increases the rate of corrosion. So some points on that. And then cathodic production. So cathodic production comes under actually corrosion control. Okay. Corrosion control. Sorry, cathodic production comes under corrosion control. So in the last video, we have told corrosion can only be controlled. Corrosion cannot be fully avoided. So in that, cathodic production is one of the important ways of controlling the corrosion. Okay. First, before we see the different types of electrochemical corrosion, we will summarize the chemical corrosion and electrochemical corrosion in the form of difference between them. So what is chemical corrosion? What is electrochemical corrosion? Chemical corrosion is also called dry corrosion. Electrochemical corrosion is also called wet corrosion. All those things we see. Now we see the differences. Okay. Chemical corrosion, it occurs in dry condition. Whereas electrochemical corrosion, it occurs in the presence of, chemical corrosion, it occurs in dry condition, whereas electrochemical corrosion, it occurs in the presence of moisture. Okay. And chemical corrosion is due to direct chemical attack of metal by the environment, whereas electrochemical is due to the formation of large number of anodic and cathodic parts. Okay, even a homogeneous metal surface gets corroded. Okay, that means only one metal, only iron or only copper, like that. Whereas heterogeneous, bimetallic is required. Okay, heterogeneous, that is bimetallic surface alone gets corroded in electrochemical corrosion. Corrosion products accumulate at the place of corrosion in chemical corrosion. The products after the that corrosion products, oxidized products, accumulate at the place of corrosion, whereas in electrochemical, corrosion occurs at anode while products are formed elsewhere. Okay. Due to the we have seen in the mechanism that the anode electrons released in the anode is taken by the cathode, and all those things, yellow rust is forming. All those things we have seen. Chemical corrosion is self-controlled process, whereas electrochemical corrosion is a continuous process. And chemical corrosion adopts adsorption mechanism, whereas electrochemical follows electrochemical reactions. We have told already that we are well known that oxidation is nothing but electrochemical equivalent of oxidation. Formation of mild scale on iron surface, which is rust, is an example. Okay. Formation of mild scale on iron surface is an example for chemical corrosion, whereas rusting of iron in moist atmosphere is an example of electrochemical corrosion. We have told that Fe converts to Fe2+, which further converts to Fe3+. And the rust formula for rust is Fe2O3 dot X H2O. That is the formula for rust, iron rust. Okay, there are two different types of electrochemical corrosion. One is called galvanic or bimetallic corrosion, and another is called differential aeration or concentration cell corrosion. Okay. First, what is galvanic corrosion? When two dissimilar metals, means the two electrode potential of the metals are different, means they vary in a big way. Okay. Example, zinc and copper, we have seen galvanic cells. When they are electrically connected and exposed to an electrolyte, the metal higher in electrochemical series undergo corrosion. That means more negative potential will undergo the reduction potential. Metal having more negative reduction potential will undergo oxidation. That means undergoes corrosion. So in the above example, zinc undergoes corrosion, copper acts as a cathode, and it undergoes reduction. Okay. So it is similar, zinc gives Zn 2+ 2 electrons, whereas copper will take the 2 electrons, okay, and acts as a cathode. Okay. So in electrochemistry, we have seen electrochemical series, whereas in corrosion, we say galvanic series. So galvanic series is slightly different from electrochemical series, which has relation to it, but it's not entirely the same. What is galvanic series then? Galvanic series are the metals are arranged from more reactive, less passive to less reactive, high passive. Okay, like that. For example, one end contains noble metals, which doesn't undergo corrosion. The other end above contains magnesium, aluminium, zinc, and their alloys, like that. So, metals and their alloys having more negative potential will be in the one end, and the other end you have noble metals like Au, Ag, platinum, like that, and their alloys which doesn't undergo corrosion. Okay. So that series is called galvanic series. Okay. Example, steel screws in brass marine hardware, lead antimony solder. One more thing, this galvanic series is arranged under the corrosion in marine condition, that means in a salt water condition. So in salt water, corrosion is maximum. So different metals and their alloys, how they undergo corrosion, based on that the galvanic series is made. Okay. Lead antimony solder around copper wire. Okay. It's not wise, copper wire. Okay. Steel propeller shaft in bronze bearing. These are all will undergo corrosion due to galvanic corrosion, due to huge difference in the reduction potential of the two metals. Either you can say galvanic corrosion or bimetallic corrosion. Okay. Steel pipe connected to copper plumbing will undergo corrosion due to bimetallic or galvanic corrosion. Next, concentration cell corrosion. It is due to electrochemical attack on the metal surface exposed to an electrolyte of varying concentrations or of varying aeration. Okay. So it occurs when one part of the metal is exposed to a different air concentration from the other part. So this causes a difference in potential between differently aerated areas, and normally it is experimentally proved that less aerated area acts as an anode, and more oxygenated areas acts as a cathode. So example, the metal part partially buried in soil, means the buried portion of the metal has less oxygenated, whereas the totally exposed to air that has a more oxygenated. So due to this difference in oxygenated areas, there will be a electrochemical concentration cell develops anode cathode, and due to that this corrosion happens. That's why it is called concentration cell corrosion. Example, one example we have seen, metal part partially buried in soil. Another one is metal part immersed in water or in a conducting liquid. is called waterline corrosion. For example, a metal part is dipped into a conducting liquid. Okay, zinc rod in zinc chloride solution, Zn2 plus. Okay, this is more. One is inside. This portion is inside the water. Some portions are outside the metal. Some portion is immersed inside the zinc chloride. Some portion is outside. So the outside is more oxygenated part, which acts as a cathode. The part which is inside the liquid is less oxygenated part, corroded, which is anode. Okay. So zinc gives Zn2 plus plus 2 electron. Okay. In the cathode, these electrons are taken by oxygen and reduced to 2OH minus. Okay. And corrosion happens at the water line. In this position, in these places, corrosion happens, which is the line difference between these two concentration of oxygens. So this is called water line corrosion. Okay. At anode, corrosion occurs less aerated. Okay, the reaction, metal undergoes metal 2 plus ions plus 2 electrons oxidation reaction. Cathode, OH minus ions are produced, more aerated. Okay, oxygen gets reduced to OH minus. Example for this type of concentration cell corrosion or pitting or localized corrosion, crevice corrosion, pipeline corrosion, corrosion on wire fence. All these things are example of oxygen concentration cell corrosion type of wet corrosion, okay, or electrochemical corrosion. Okay, next, generally some of the points which can affect the rate of corrosion, factors affecting the corrosion. So basically there are two types. One is due to nature of metal. There are some reasons, and another one is due to nature of the environment. So there are two effects. One is due to nature of the metal and another is due to nature of the environment. So first we will see the nature of the metal. The rate and extent of corrosion depends on the following factors: purity of metal, position in the galvanic series, over voltage of hydrogen, nature of oxide film, nature of corrosion product. So these are all related to metal, purity of the metal, position in the galvanic series, okay, over voltage, nature of oxide film, and nature of oxidation product, corrosion product. Okay, purity. Say normally heterogeneity of the metal, that means metal having some impurities, okay, will undergo more corrosion because it forms tiny electrochemical cells at the exposed parts. Okay, if the metal is pure without any heterogeneity, it doesn't undergo corrosion. Electrode potential. So obviously metals with higher reduction potentials do not corrode easily. So they are noble metals like gold, platinum, silver. Whereas the metals with lower reduction potentials readily undergo corrosion. Zinc, magnesium, aluminium. So these are all called active. Zinc, magnesium, aluminium are called, they are anodes. They are acting as anodes and they are highly active. Whereas gold, platinum, silver are passive. They are not very active. In fact, they are noble. They doesn't undergo corrosion. Okay. Position of metal in galvanic series. This is electrode potential. And where it is positioned, if the position of the two metals or wide difference is there, it undergoes corrosion. If they are very closer, next to next, then it undergoes less corrosion. So metals which possess low reduction potentials and occupy higher end of galvanic series undergo corrosion easily. Okay. So when two metals are in electrical contact in presence of an electrolyte, then the metal which is more active undergoes corrosion, okay, because it is more anodic, more active. The rate of corrosion depends on the difference in their position in galvanic series. Greater the difference, more will be the corrosion rate at anode. Another, relative areas of anode and cathodic cells. So we have seen already in the mechanism, when two dissimilar metals or alloys are in contact, the corrosion of the anodic part is directly proportional to the areas of the cathodic part. So the ratio of relative areas of corrosion is influenced by the cathodic to anodic cells. See, for example, larger the cathode and smaller the anode, the reaction rate is more, because cathode takes the electron from anode. So anode has to provide that much electrons for the bigger cathode. So it has to undergo more corrosion in order to give the electrons. So the reaction corrosion rate increases if anode size is smaller and cathode size is bigger. Physical state of metal. Metals with small grain size have more tendencies to undergo corrosion. Metals with more stress or strain also undergoes corrosion easily. Okay. So next, hydrogen overvoltage. When a cathode reaction is hydrogen, we have seen hydrogen evolution, one of the type of cathode reaction. The metal with lower hydrogen overvoltage value on its will undergo more corrosion because of liberation of hydrogen gas is easy at this condition. Okay. Hence, the cathodic reaction is very fast, which in turn makes anodic reaction faster. Okay. Hence, the rate of corrosion increases. Higher the overvoltage, lesser is the corrosion. Nature of surface film. If the corrosion product found is more stable, insoluble and non-porous, it acts as a protective layer and prevents further corrosion. For example, titanium, aluminium, chromium, etc. Alumina and chromium oxide films formed over the metal surface acts as a protective layer, means it protects the further corrosion of the metal because it is uniform, stable. So it acts as a protective layer. It prevents the further interaction of oxygen with the surface of the metal. Okay. Nature of environment. So obviously we have temperature. The rate of corrosion increases with the increase in temperature. Humidity in air. If humid conditions are more, corrosion rate increases. Presence of impurities. So obviously presence of atmosphere contaminated with impurities like impurity gases or fumes of this and other suspended particles. They are responsible for electrical conductivity and increases the corrosion. pH value. pH value of the medium has greater effect on corrosion. Acidic pH increases the rate of corrosion. Obviously, amount of oxygen in atmosphere. As the percentage of oxygen in the atmosphere increases, the rate of corrosion also increases due to the formation of oxygen concentration cell. Okay. Velocity of ions which flow in the medium. Velocity of the diffusion of ions in the medium. For example, oxygen is diffused into the metal. So if that velocity of ions are more, then also rate of corrosion increases. Okay. So next we go to corrosion control by Cathodic Protection. Okay. So the various measures taken for corrosion protection are cathodic protection and surface coatings. Okay. So today we will see cathodic protection, what it is. Cathodic protection means the method of protecting metals and alloys from corrosion by making them completely cathodic. So how will you make the metal to be protected as a cathode? To achieve that, we have to add auxiliary anode. Okay, we have to provide an auxiliary anode in the corroding medium, which is connected to the main structure to be protected. Okay, so thereby cathodic protection can occur to the metal to be protected. So cathodic protection is of two types. One is sacrificial anode method, another one is impressed current method. So what is cathodic protection? It forces the metal to be protected to behave like a cathode. Okay. So first, sacrificial anodic protection. So metal to be protected from corrosion is connected to a more anodic metal. Okay. For example, iron, steel bodies made up of iron, if it is connected to highly anodic magnesium or zinc or aluminium and their alloys, the steel body is prevented from corrosion because by connecting it to more anodic and more active magnesium or zinc or aluminium and their alloys, the steel structure has become cathode. Okay, all the corrosion happens with the auxiliary anode, which are more reactive than the steel, which contains iron. Okay, so thereby, from the word itself, it is sacrificial anode. The anode you use will undergo reduction, and metal structures like steel structures are prevented from corrosion. Okay, for example, a ship hull which is made up of steel is connected to a sacrificial anode, zinc blocks, for example. The zinc blocks undergoes corrosion, leaving the base metal protected. That means steel. The ship hull made up of steel is prevented from corrosion. Similarly, another example, the underground water pipelines and water tanks are also protected by sacrificial anode method. Okay, so here also by connecting the auxiliary anode, which is more active, more anodic than the base metal, which has to be protected, we can avoid the corrosion in the main interest area, and anode, auxiliary anode, which you connected to the metal, will undergo instead corrosion. That's why it is called sacrificial anodic protection. Okay. Next, okay, this is the diagrammatic representation where in unprotected metal being corroded, we have cathodic sites, anodic sites, anode to cathode electron. So this is the just unprotected, and now protected base metal. You want to prevent corrosion in this place. So now you bring sacrificial anodic protection. You connect this area to be protected to the another auxiliary anode. Now this corrosion occurs here in the auxiliary anode, and this main base metal which needs to be protected from corrosion is protected. Okay, the purpose of adding the auxiliary anode is done by avoiding the corrosion here. Okay, so that's why it's called sacrificial anodic protection. So similarly, below the ship hull, below water. Okay, so we have seen these examples where zinc or aluminium or magnesium, more anodic part, is connected to the metal structure. So anodic part, auxiliary anode, will undergo corrosion. This is called sacrificial anode, zinc or magnesium or aluminium, and the base metal is protected because in the presence of this highly anodic active metal, the base metal itself became cathode. That's why it comes under the category of cathodic protection. So another one is impressed current method. So here direct current is applied in opposite to nullify the corrosion current. Okay, what is meant by corrosion current? When anode undergoes corrosion, that means when anode undergoes oxidation reaction, it releases electron which is moving towards cathode. So that is called corrosion current. So here in this impulsed current method, you apply a current in opposite to this current, more than the corrosion current. You apply the direct current in opposite direction to nullify this corrosion current. Okay, it converts the corroding metal from anode to cathode. Okay, so in this method, an impressed current is applied in opposite direction to nullify the corrosion current and convert the corroding metal from anode to cathode. The impressed current is slightly higher than the corrosion current. Thus, the anodic corroding metal becomes cathodic, and protected from corrosion. Obviously, the impressed current is taken from a battery or a AC, like a rectified on AC line, etc. The impressed current protection method is used for water tanks, water and oil pipelines, transmission line towers, etc. Okay, transmission line towers, etc. All those things are prevented from corrosion by impressed current method. Okay, so this is the diagrammatic representation of impressed current. There is a pipe, okay, pipe, and then you have a anode here. So this is the pipe cathode. This is the galvanic anode. So now the current from corrosion current comes from anode to cathode, whereas you supply a DC current in opposite. That is called impressed current. So thereby making this anode as a making this metal as a cathode. Okay, or this obviously this metal pipe which has to be protected will be made cathode because of impressed current supply. Similarly, we have this is ground surface. These are all below ground we are talking. Okay, under the ground, pipeline underground. So here ground surface and below protected pipeline. Okay, by supplying current, it has become cathodic. Okay, direct source through wire current, impressed current is passed, and then protective anode. Okay, so by this impressed current method, we make the part which has to be protected to be made as a cathode. So thereby we are protecting the metal to be protected by cathodic protection. So impressed current method, we are applying current opposite to the corrosion current, or more impressed current compared to the corrosion current. Okay, so we will see with this cathodic protection is over, and we will see further corrosion control methods, surface coatings, and all those things in the next tutorials. Okay.
Like, share and subscribe. Hit the bell icon for more updates.